Welcome everyone to the afternoon session of this next day of conference. So for our first talk, we are honored to have Adlam from Chapman University who's going to tell us about Quiddities versus quantum mechanics.
Hi everyone. Thank you very much for the organizer. Great to be here. I was glad to see this conference. I was kind of working on this project and thinking, where am I ever going to present this? Who's ever going to care about this? So stars aligned with people who hopefully do care about this. So what I want to talk about is Quiddities. Oh, I don't know. It's magic. I want to talk about Quiddities. I've been worried about Quiddities for a while. It's quite common to object to Humeanism on the basis that it requires Quiddities, but various other approaches to laws of nature arguably also seem to require Quiddities. So in particular, I've worked in the last few years on constraint views of lawhood, and certainly in the way that I formulated that, and in the way that other people have formulated that as well, that also seems to require Quiddities. I think that's bad news, and so I'm interested here in looking at if various approaches to general relativity and quantum gravity can give us some better ideas about how to get rid of Quiddities, and hopefully thus give better formulations of the constraint view as well. So I'll start with some methodological comments. I'll then say why I don't like Quiddities. I'll then talk about two different possible ways of getting rid of Quiddities, one the contingent approach and one the necessitarian approach. Basically the message here is going to be that all of the contingent approaches seem to lean very heavily on giving space-time or spatiotemporal relations a privileged role. That seems like a problematic thing to do in the context of both GR and quantum gravity. So that pushes me more towards the necessitarian views, but there are some open questions about how to actually make the necessitarian views work. And I think that GR and quantum gravity themselves can give us some clues about how that might look. In particular, the notion of an internal view plays a really important role here and can help us see perhaps how to solve this Quiddity problem. So methodologically speaking, I'm mostly here just going to try to read metaphysics of some existing formalisms, so the partial complete observables formalism and the quantum reference frame formalism. Obviously in practice that would also have to be balanced with sort of empiricist considerations regarding how likely those theories are to actually be right. But the sort of more general point I want to make is that even if these approaches are not in fact right, I think nonetheless they offer some useful ideas about how to do the metaphysics of modality, and so there's something to be learned here, kind of regardless of whether or not these theories are actually right. This does mean that the result is going to be somewhat limited in scope. The account of modality I'll suggest here is going to be suitable for worlds whose observables are sufficiently similar to what we see in the partial complete observables formalism, but not appropriate for necessarily all possible worlds. That rules out certain quite general ways of thinking about the relationship between modal and non-modal features of reality. So in particular, Chapman suggests thinking about this as a question about which possible worlds one should countenance. That's not really going to be a useful way of thinking in the kind of approach I'm taking, because the result is going to depend quite sensitively on what the laws are of the world that you're dealing with. That to me seems reasonable because I'm skeptical that it's possible to give a fully general account of the relation between modal and non-modal features of reality without sort of referring to the specific nature of the modal structure you're dealing with. So I'm kind of happy with the consequence that it's going to be relativized in some sense to what kind of modal structure you're dealing with. Okay, so Quiddities. Quiddities are ways of thinking about properties where we understand them as intrinsic essences that are independent of any facts about their function. So for example, if we think about mass, if you understand mass as a sort of intrinsic property which could have been subject to different laws and would still have been mass, that means we're thinking about it as a quiddity. It's not defined by its role in the laws, it is a thing in and of itself independent of those functional facts. The sort of opposite view is to think about properties in more structural terms, so think about properties as being defined by the role that they play in various nomic or modal structures. So it's fairly straightforward to see that if you think that properties are defined in advance of laws and other modal features, and you also think there's more than one kind of property, we're going to need something like quiddities because we're going to need to have some way of distinguishing those different types of properties, and we can't do that by appeal to laws or other sort of structural features if the properties come before the laws. So that means that most Humeans are going to require quiddities. The Humeans want to define a Humean mosaic and then define the laws as patterns in that mosaic. That means they need to use quiddities to define what properties are and where they are in the mosaic in advance of arriving at the laws. So one common objection to Humeanism is precisely the fact that it seems to rely on using quiddities. But constrained views of lawhood, like I have worked on and Jen and Goldstein have worked on, also seem to require quiddities. That's because both of us defined constraints extensionally as something like sets of Humean mosaics. So to do that, we need to have quiddities in order that we can define mosaics of properties across space-time and then define constraints as sets of them. So it looks like we are sort of dependent here on some notion of quiddities. That, I think, is bad news. I think there are a lot of reasons to think we shouldn't like quiddities. One worry is that if there are quiddities, then two worlds can share all of their functional and behavioural features, yet differ only in terms of their quiddities. So, for example, there could be another world just like this one, except that mass and charge have been swapped, but nothing else is different. That seems undesirable because it's just a bunch of kind of superfluous structure that isn't really doing any explanatory work, but which nonetheless gets put in there. So if we can get rid of that kind of superfluous structure, that's probably a good thing to do. There are also epistemic concerns. If there existed two properties with distinct quiddities but they shared a causal profile, we could never possibly distinguish between them. They would be the same to us for all effects and purposes. And so again, it's kind of not clear what role quiddities are playing if we have this very limited epistemic access to them. And perhaps most importantly, science just doesn't care about quiddities. Scientists have no interest in trying to figure out what the quiddities are. When we use properties in science, they're introduced functionally in terms of their role in the dynamics. Mass, for example, is introduced through its dynamical role as dynamical parameters that couple particles. So insofar as it's a good idea to do metaphysics in a way which is informed by the way science is actually done, we have pretty good reasons to think we shouldn't be relying too much on quiddities. So, if we want to get rid of quiddities, what are the options? Basically, there are sort of two different classes of response here. The first is to say that there's a connection between modal and non-modal features is contingent. The second is to say the connection between modal and non-modal features is necessary, leading to some kind of structuralism about properties and relations. I should say that throughout this talk I'm going to use the word modal as kind of a general term which subsumes nomic structure, causal structure, various other, whatever other kind of sort of not additional structure you might have here. So I'll just use modal to sort of refer to all of those things in a general way. Okay, so there are various different contingentist approaches you might adopt, but they all have one thing in common. If you want to get rid of quiddities while maintaining there's a contingent relation between modal and non-modal features, really the only possible way to do that is to say there's just one kind of fundamental non-modal thing. That's because if there were more than one kind of fundamental non-modal thing, you would then have to use quiddities to distinguish between those things. So all of these approaches work by identifying one special non-modal thing. And specifically, all of them end up going down the route of making that special non-modal thing spatiotemporal. Space-time seems to be sort of presumed by everyone as the obvious, basic, non-fundamental thing to use here. So for example, superhumanism is based on adopting a very minimal ontology, which consists of only massless matter points and relative distance relations. These massless matter points are moving around in various ways, and then, in the traditional Humean style, the laws of nature are going to be identified as the axioms of the best systematization of the motions of those massless matter points. So in this picture, fundamentally the connection between the laws and the non-modal features is contingent, since different configurations of the matter points with different distant relations will give rise to different laws. There is a sense in which some higher level non-modal features could be thought of in structuralist terms, so mass, charge, and so on are just going to appear in this picture as like parameters in your best system. So in some sense, a necessitarian approach for those kinds of properties is possible in this picture. But nonetheless, fundamentally speaking, the connection between modal and non-modal stuff is contingent. So as I say, this only works because they have this picture in which there is only one kind of fundamental non-modal thing, and in this case it is relations of relative distance. Those relations are given a special role. They're the only kind of property or relation which is allowed to exist fundamentally. So there are questions about whether this can be made to work technically. It's not clear that you get enough structure here to really obtain the whole world. Putting the technical stuff aside, I have some sort of conceptual worries about this idea of treating space-time relations as really special in this sense. One worry is that the kinds of arguments typically used for structuralism about properties also seem to apply just as well to features of space-time. So the space-time functionalists, for example, have noted that our understanding of what space-time is seems very closely linked to the role that space-time plays in various kinds of laws. It's not clear that it would really make sense to call something space-time if it didn't feature in those kinds of laws. In addition, I think a lot of what's going on here is people are relying on an intuition like the one expressed by Pythagorean, which is that, sure, certain kinds of properties like charge do seem like they should be understood in structuralist terms, but position is really special. Right? Position is different from all the other kind of properties, and so it's fine to treat that in a non-structuralist way, even if everything else is being understood in a structuralist terms. But that seems not very consistent with what's going on in general relativity. In theories with a dynamical space-time, relations of relative distance are dynamical just like anything else. It doesn't seem to be a very good reason to treat relations of relative distance as this sort of special thing which has this privileged role when everything else is being treated structurally. So it is, of course, formally possible to get a dynamical space-time out of a superhuman picture. It's not sort of a formal problem. But what happens is that if you're doing that, the dynamical nature of space-time ends up just being a contingent fact about the actual configuration of relative distances and the best system you arrive at to describe them. So it can kind of be made to work, but it seems to me that this doesn't fully respect the relativistic understanding of space-time. I would have thought that the dynamical nature of space-time is like really essential to what space-time is in the kind of picture we're seeing in these theories of dynamical space-times. So I'm skeptical that it really makes sense to go down a route which says it's just a contingent fact. Furthermore, of course, things are going to get much worse if space-time is not even fundamental at all, as in some theories of quantum gravity, like quantum gravity. Certainly, if space-time is not fundamental, then relations of relative distance cannot possibly be the one fundamental non-modal thing, and so some other kind of route is going to be necessary. So I don't want to claim that superhumanism is impossible and incompatible with these kinds of theories, but I think at a conceptual level there are reasons to be worried, and so there are good reasons to see if there's any way to get rid of quiddities without treating relations of relative distance as this special privileged thing. Another contingentist approach is something like dispositional essentialism. So this would involve having a basic ontology constituted of objects which are possessed of modal properties. This leads to the same kinds of problems. The reason for that is that obviously these objects have to be individuated in some way before you can assign modal properties to them. And if we're not using quiddities, then they can't be individuated by non-modal properties because we don't have any non-modal properties before we start assigning the modal properties. So that suggests that we're going to have to be individuated by something like space-time position or spatial space-time relations. So again, in this picture, space-time has been given a special role as the fundamental non-modal thing. So for the same reasons as before, I think we should be worried about this as worth trying to see if we can get rid of quiddities without doing that. In addition, I have the worry that many modal structures we see in modern physics are quite global. They don't look very easily reducible to properties of individual objects, and so that makes the dispositional essentialist view look not very appealing. So I'm skeptical that any of the contingentist approaches can work if we're really determined to not treat space-time as special in this way. So let's have a look at some necessitarian views instead. So the necessitarian views say that the connections between modal and non-modal features of reality is in some sense necessary. So one example of that might be a version of modal onto structural realism in which there are no fundamental objects and there are no fundamental non-modal properties, only modal structure is fundamental. In that case, clearly the properties can be understood in structuralist terms. They are going to be what they are in virtue of how they arise from the modal structure. So I do find this quite appealing as an approach, but there are some outstanding problems in trying to understand exactly how modal and non-modal features are actually connected in this picture. So obviously, in some sense, at some point, we're going to have to explain how our ordinary experience of a world filled with apparently non-modal properties comes about if, in fact, only modal structure exists fundamentally. There's also the sort of usual problem for object structural realism that it seems perhaps conceptually difficult to understand how there can exist relations or structures without sort of relata to stand as the nodes in those structures. And in the modal case specifically, it seems perhaps a bit unclear how an actual object is supposed to be able to arise from a modal structure. If you think of modal structures as characterizing possibilities in some sense, there's a sort of open question about how actuality is supposed to emerge from just possibilities. So I think all of these problems can potentially be addressed. I will come back to this shortly and argue that the partial complete observables formalism perhaps offers some way to resolve these questions. But first I'll talk about a couple of other necessitarian approaches. So another necessitarian approach is Lower's package deal account, which is a Humean view. So Lower wants to get rid of quiddities by arguing that not only the laws but also the objects and properties all come from the best system. So his thought is that all of those things come from the best system altogether as a package deal, so we don't need quiddities because we're not trying to define properties in advance of the laws. So that sounds appealing. The worry is if the properties don't exist in advance from the law, in advance of the best system, what on earth does the best system systematize? So Lower's answer to that is that it just systematizes macroscopic regularities. One worry you might have there is that this is just going to end up collapsing into some kind of operationalism, but perhaps more relevantly to the current discussion, I worry that if we're doing that, then we sort of still do end up needing quiddities. We just end up having to have macroscopic quiddities rather than microscopic quiddities. So simply moving all of the systematization to the macroscopic world doesn't necessarily get rid of this problem of needing quiddities. It just kind of moves around the way that what quiddities are going to be located. So although I like the idea of laws, objects, and properties all being defined together, I'm not sure that's going to work within a Humean picture. Finally, we have the view called moderate object structural realism, which is used against Adlam. They suggest a view in which relations and objects are on the same ontological footing. They're given at once in the sense that they are mutually ontologically dependent on each other. So again, I do find this appealing, but I think it's a bit harder to understand in the case where the structure and relation is modal in nature. It's perhaps not intuitive to see how it is that modal and non-modal features could just be aspects of each other. So Isabel and Landu suggests an approach inspired by Spinoza's view of properties as modes of existence, where we say that a structure consists of objects whose ways of existence are certain relations that they bear to each other. So that I can sort of see how that might work in the case where the structures are non-modal structures. It seems perhaps less obvious how it works in the case where they are modal structures. If we think we have a structure consisting in possible objects whose possible ways of existence are certain relations that they bear to each other, it's still not obvious how we then convert these possible objects into actual objects in order to arrive at the actual world as we experience it. So again, I find this appealing, but I think there are still some questions about how exactly the non-modal stuff is supposed to come out of or be related to the modal stuff. Okay, so just to sum up, I would like to get rid of quiddities. I'd like to do that without having to treat space-time as a sort of special privileged thing. I'm not convinced that can be done within a contingentist approach. I do think that there are appealing and promising ideas within the necessitarian pictures, but there are still outstanding questions about how exactly we're supposed to get the non-modal stuff out of the modal stuff in these necessitarian pictures. So what I want to do now is argue that the partial complete observables formalism and the quantum reference frame formalism can give us some interesting new ideas about how non-modal stuff could emerge from modal stuff. So just to briefly introduce the partial complete observables formalism, as we all know, the standard way of interpreting a diffeomorphism in variant theory is to say that histories related by a diffeomorphism are physically identical. That implies that variables which can be expressed as local functions of the coordinates are not observables, i.e. they are not physically real. So one obvious consequence of that is that it seems to rule out at least the most naive version of Humeanism, the version which has a mosaic of categorical properties distributed over space-time. But there are presumably ways in which you could imagine a more sophisticated Humeanism. So rather than just immediately rule out Humeanism, I want to look more closely at the relation between modal and non-modal stuff as the formalism understands it. So the formalism has what appears to be a pretty serious problem. Nearly everything that we actually observe sort of seems like it is a local function of the coordinates. So if local functions of the coordinates are not physically real, how can we understand the nature of the observables we actually observe in this kind of picture? So Ravelli suggests addressing this using the formalism of partial and complete observables. So what he does is he distinguishes partial observables, which are physical quantities to which we can associate a measuring procedure into a number, from complete observables, which are diffeomorphism invariant and hence physically real. So the thought is partial observables are the kinds of things we actually observe. Complete observables are the things that are physically real according to the diffeomorphism invariant formalism. So how can that be? How can it be that the things we observe are not physically real? Well, the thought is that the relations between partial observables are complete observables, so those relations are physically real, and thus, roughly speaking, it seems that an observer can observe a partial observable in virtue of it being relativized to her, or a measuring device can measure a partial observable in virtue of it being relativized to that measuring device. So, for example, in the case of position, we're not actually observing absolute positions, we're observing positions relativized to our own location. So that allows us to kind of identify those things and make observations of them, even though they're not in some sense physically real. So one thing you might say about the partial complete observables formalism is that it looks like a nice fit for some kind of ontic structural realism. So in particular, Rickles suggests that this formalism is a useful way to solve the no relations without the latter objection for structural realism, because it does appear that in the partial complete observables formalism, we are presented with a physical theory in which, indeed, the relations are kind of the only fundamental thing. The relata, the partial relations, are not physically real in and of themselves. They are ontologically dependent on the underlying relation, and they can't exist without that relation. So here is a formalism in which it really is true that we have relations and that relata exist only insofar as they are dependent on those relations. So this looks like a promising sort of formalism to use to investigate the possibilities of ontic structural realism. So if we agree that we're dealing with some kind of ontic structural realism, the next question is, what kind of structure is this? Is this modal structural realism or some other kind of structure? So if we go, I'll consider the classical case first and then talk about the quantum case. Looking at classical GR, we have two main classes of physically real observables, highly non-local quantities defined over the whole space-time, and differently non-local relational quantities built up of correlations between field values. So the latter kind of observables are the ones which are usually assumed to ground out sort of observations of local observables, so I'll focus on those here. So Ravelli gives an example of that kind of relational observable. He considers a case where we have Venus making an angle with the horizon and the Sun making an angle with the horizon. He notes that, of course, we can't just predict the Venus angle or the Sun angle individually. We need to have some kind of index or label saying when we are interested in it. But what we can do is predict the Venus angle as a function of the Sun angle or vice versa. So we can predict the relations between them. And so he argues every possible pairing of a value for the Venus angle and the corresponding value for the Sun angle is a complete observable. So, for example, one complete observable is the value of the Venus angle when the Sun angle is 5. So what should we say about the nature of the structure that is instantiated by these kinds of relational observables? Well, Ravelli tells us that they are built on correlations, but this word correlations sort of has two different possible meanings. We can understand the term correlation as referring to properties that are exhibited over some real ensemble, or we can understand the term correlation as a sort of modal statement making some claim about what the value of one variable would have been if the value of the other variable had changed. So if we're trying to use the ensemble view in Ravelli's example, the ensemble view would see the observable as a collection of sort of coincidence events. We would see a collection of events of the kind, value of the Venus angle for the Sun angle equals 0, and the value of the Venus angle for the Sun angle equals 1, and so on and so forth. So you might at first think the observable we're dealing with is just an ensemble quantity referring to all of these separate coincidence events. But we should be careful here because the relation between the correlation and the events is not really like in pre-relativistic physics. In pre-relativistic physics, what you might have done is write down one trajectory, write down the other trajectory, then write down all of this sort of sequence of coincidence events, and then calculate the correlations between them. But we can't do that in relativistic physics because we can't express those two trajectories independently from each other. The point that's being made here when thinking about this in terms of complete observables is that we have to sort of start from this function, giving the value of the sun angle as a function of the Venus angle, and from that we can derive a set of coincidence events which are underwritten by this function. So basically, in this kind of relativistic picture, the correlation really comes first. The ensemble description is necessarily parasitic on the underlying modal connection that is encoded in this function that gives one in terms of the other. So that to me gives good reason to think that what's going on here is that we're dealing with some kind of modal structure, and the connection between these two things is fundamentally a modal fact encoded in this correlation. It's not just a description of the ensemble because the ensemble necessarily follows the underlying connection. So that suggests to me that insofar as you think that the partial complete observables formalism is a form of ontic structural realism, what we're dealing with is some kind of version of modal ontic structural realism. What about the quantum case? So it's not very easy to derive actual observables from existing theories of quantum gravity. So rather than using a particular theory of quantum gravity, I'm going to try to get some intuition for what's going on here by using the quantum reference frame formalism. This formalism arises from generalizing the sort of Page-Wooters approach, which is designed as a solution to the problem of time and quantum gravity. So basically, it has a similar kind of idea to the partial complete observables approach. Thought is that physically meaningful variables are going to be defined relative to some internal reference frame. You choose a physical system, and once you have done that, you can then describe meaningful variables relative to that. So sort of formally speaking, this proceeds by starting from some global state, presumably the solution to the Wheeler-DeWitt equation or similar. Then we can perform transformations on it to extract from it various different statements of the general form. System X is in the state psi I relative to the clock being in the state ti. So we get relative states of one system relativized to the state of another system. So in particular, one thing you can do in this formalism is show that the relative state of system X relativized to some clock is going to undergo sort of standard Schrödinger evolution relative to the regions on the clock, so you can obtain some kind of quasi-temporal evolution inside this relative description. So what kind of structure is being expressed here? So again, the observables in this picture are correlations, right? We have a global state psi, and we can obtain from it various statements of the form. The system is in some state psi I relative to the clock reading ti, and so on. And again, as in the classical case, the correlation really comes first, and the individual events are derived from that correlation. So again, it looks like we're not really dealing with an ensemble here. We're dealing with an underlying modal connection from which the ensemble can be derived. Now, in the classical case, I think it's plausible to say that, in some sense, the connection between the individual events was just spatio-temporal, so that perhaps undermines slightly the idea that we're dealing with modal structure. In the quantum case, though, the modal nature seems much stronger. So, in particular, when we make a statement of the form, the system is in state psi I relative to the clock reading ti, it's not clear that that connection being expressed there is really spatio-temporal at all. In particular, this phrase relative to. It's not totally clear in this formalism what relative to is supposed to mean, but what it certainly doesn't mean is at the same time as. We're not just saying the system is in state psi I at the same time as the clock reads ti, because the whole point of this formalism is that time is going to be extracted from these kinds of relational observables. So it looks like the nature of the connection expressed by this phrase relative to is some other kind of connection, some non-spatio-temporal connection. And it seems plausible to me that we should think about this connection as being a modal connection, that it's expressing some kind of nomic or other kind of modal structure. So again, there's even stronger reasons here to think that insofar as this is a form of ontic structural realism, it needs to be understood as a kind of modal ontic structural realism. Okay, so that's good news, right? Because the partial complete observables approach and the quantum reference frame formalism look like they are quite good real-life examples of some form of modal ontic structural realism. So we can use these examples to get a sense of how it is that non-modal properties can emerge from this kind of modal structure. And I'm going to argue that in both these formalisms, they do so via the notion of an internal view. Furthermore, I want to argue that, kind of regardless of whether or not these approaches themselves are correct, the notion of an internal view and its role in negotiating between modal and non-modal structure is a really useful idea which can plausibly help us solve the quiddity problem, kind of regardless of our sort of specific scientific commitments. And so I think this is a useful project to embark upon, even if these particular formalisms don't turn out to be right. So both of these formalisms make really essential use of the idea of an internal view, of like moving inside the universe and adopting the perspective of some particular physical system. So obviously the idea of an internal view is not new. Even in classical physics we can distinguish between a sort of external description of the world as a whole and an internal description from someone's point of view. But in theories with absolute spacetimes, right, there's really no strong distinction between external and internal views. The internal view of someone in an absolute space-time kind of corresponds to just like cutting out a small piece of the external description corresponding to the region which is perceptually accessible to them, and perhaps putting it into some state of motion. There's nothing very new that comes when you move to an internal view in that picture. But already as soon as we move to like a relational space-time, we can see that the internal view is going to introduce something quite novel, right? Because in a relational space-time, there are no positions in the external description, there's only relations of relative distance. But when you move into an internal description, positions somehow come into being, right? Once you start describing things from an internal point of view, you can assign objects around you positions which are implicitly relativized to you. So in that case, adopting an internal view has introduced some kind of novelty, right? A new kind of property has come into being that was not there in the external description. So what I want to suggest is that the partial complete observables formalism and the QRF formalism seems to implement similar mechanisms for other properties beyond just position and spatiotemporal properties. So that's because, in some sense, there are no categorical properties in the physically real external description. Everything that we would naturally describe as a categorical property gets treated as a partial observable in this formalism. So that means that when we move to an internal view relative to which we can experience various partial observables, what we're essentially doing is bringing properties into being. Things like mass, spin, and charge appear as partial observables relativized to this internal view. Those properties aren't there in the external third-person description. They only make sense in this kind of internal description. We can see that happening mathematically as well. So in this formalism, we think of partial observables as being defined on a configuration space, with complete observables living on the associated reduced space. So the partial observables correspond to extra and physical degrees of freedom, which are brought into being by adopting an internal view. So again, using an internal view introduces novelty here, brings into being something which was not there in the external description. And so my thought here is that this process of bringing properties into being by adopting an internal view is a nice way of accounting where the non-modal features come from in some kind of modal structural view. We can say that from the external point of view, all there is this kind of sort of big modal structure, but when you adopt some internal view on the universe, what that does is it brings into being various kinds of properties. Those properties, from the standpoint of the internal view, look kind of like categorical non-modal properties. That's not what they really are. From the sort of third-person point of view, we know that all that exists are these sort of relational complete observables, but in the internal point of view, these non-modal properties seem to appear. We see similar things happening in the quantum reference frame formalism as well. So in the QRF picture, there don't exist any non-relational intrinsic properties. We do have a global state psi, but the global state doesn't really encode sort of categorical properties in the ordinary sense. It's just a description of a sort of possible collection of relational states. But when we adopt an internal view by taking up the reference frame associated with some system X, we can then assign quantum states to other systems relative to X, and those quantum states behave pretty much like ordinary physical states. They appear intrinsic to the systems to which they are assigned relative to that internal point of view, and relative to the internal perspective, they're going to undergo time evolution according to the Schrödinger equation. So again, we see that by moving into this internal view, we have brought intrinsic properties into being, essentially. In the external view, there aren't any intrinsic categorical properties, but from this internal point of view, these things appear. So again, there's a sort of nice way to describe the emergence of these non-modal features. That emergence happens in virtue of taking up an internal view. Okay, so suppose we accept this as a useful picture of the connection between modal and non-modal features of reality. What should we say about the sort of metaphysics of this approach? So one thing that probably should be emphasized is that the idea of an internal view doesn't need to have anything to do with consciousness. So both of these formalisms allow us to adopt internal views defined relative to basically any physical system. So there's no need for it to be a conscious observer or anything like that. So that means that this technique for extracting non-modal properties from modal ones doesn't necessarily rely on some kind of anthropocentricism or instrumentalism or anything. It doesn't have to be a conscious observer. We can get this kind of emergence of non-modal features relative to any physical system. The other question I want to ask is, what is the sort of nature of the connection between the partial observables and the complete observables? So I'm slightly nervous about using standard metaphysical terminology to describe that connection, just because I'm not convinced that we have developed the right terminology yet. But perhaps the sort of closest thing would be the relation of common ground, which is defined by Ismail and Chapman by analogy to a common cause. So their thought is that we say two events A and B have a common cause C, if C is the cause of both A and B. And so similarly, we can imagine circumstances in which two entities, A and B, have a common ground C, if both of them are grounded by some entity C. So there is a crucial difference here between common causes and common grounds. Entities with a common cause are effectively independent, right? If both A and B are caused by some event C, you can cut off the event B and prevent B from happening, but A is still going to happen. Those are sort of independent events. But entities with a common ground are not independent because the modal connections are tighter here. If A is grounded by C and B is grounded by C, then you can't sort of get rid of B without also getting rid of A, because A and B are sort of just aspects of C. So one example of this given by Adlam and Chapman is the relationship between temperature and pressure in standard thermodynamics. Their thought here is that temperature and pressure have a common ground. They're both grounded by sort of molecular motions. And that means that you can't get rid of the property of pressure without also getting rid of the property of temperature, because you can't get rid of pressure without getting rid of molecular motions, and when you get rid of molecular motions, then you have gotten rid of temperature too. So we see this sort of tighter connection in the case of a common ground. And that seems like plausibly a feasible way of thinking about the connections between complete observables and partial observables. You can think of the partial observables as being both grounded by the complete observables, thus explaining why it is that they have this very, very tight interdependence. You can't have one partial observable without the other one, because they exist in virtue of this relation between them that grounds them, and so you can't get rid of one without getting rid of the other. Okay, so finally I just want to take a step back and ask what this internal view approach might tell us about lawhood and how to think about it. So in particular, I would argue that in addition to hopefully getting rid of quiddities, this approach may also help resolve some questions that you might have about laws. So if we look at the sort of Humean versus non-Humean debate, perhaps the big source of contention there is about the issue of how it is that laws explain things. The Humeans are often accused of having the problem that Humean laws can't really be explanatory. But then again, in the non-Humean approach, it's still perhaps arguably a bit mysterious how laws actually constrain things, so in some sense, there's still an explanatory problem there. I think that thinking about properties as just views on modal structure, as being brought into being by taking some kind of internal view on modal structure, can maybe help with some of those issues. If properties are just views on modal structures, then it seems obvious that the modal structures do explain why the properties are the way they are, because they are the way they are in virtue of how they arise from those modal structures. Similarly, if properties are just views on modal structures, then it's obvious that the modal structures must constrain the properties, since the properties are limited by the available views. So this is ongoing work, but I do think that there are promising ideas here in terms of how to think about lawhood and explanation in terms of the relation between properties and modal structures. Okay, so just to sum up, I was worried that the constrained view of lawhood is too dependent on using quiddities. Interested, therefore, in seeing how to get rid of quiddities. the approaches which try to do that by giving contingent connections between modal and non-modal features all seem to have the problem that they require us to treat space-time or relations of relative distance as like special and fundamentally privileged in some sense. So that makes the necessitarian approaches look more appealing, but existing necessitarian approaches seem to have problems with accounting for the way in which non-modal features could emerge out of modal features. I think that the approach taken in the partial complete observables formalism and the pure formalism offers a really nice way of kind of resolving that issue, because this methodology of taking an internal view sort of shows how you can bring properties into being from a structure that doesn't have properties, and thus gives us a nice way potentially of obtaining non-modal properties out of modal structures. With that, thank you for listening, and I'll see you next week.
We use the same convention as this morning, so hand for a question and finger for a follow-up. So we start with Baptiste.
Thanks, very interesting. A question on metaphysics of internal views. You use the expression, this idea of bringing into existence the properties.
Yeah.
It seems to be temporally flavored a bit. And I was wondering, do you want exactly this notion of bringing into existence, or would you be open to perhaps relate notions like ontological dependence and just like those properties, they depend on those particular views, without saying that there is this kind of directional oomph of bringing into existence?
So I guess I was using bringing into existence a little bit metaphorically, but also to describe, if you are doing the math, you might start from an external description and then move into an internal description. And so, in that sort of sense, mathematically, it will look to you as if you have brought into being these properties. But yes, I don't want to assume a sort of that the properties actually come into being in some temporal order, because obviously, in this kind of picture, the internal and the external views all sort of coexist together. We don't move, the world itself doesn't move from the external description into an internal description. It's just that we might do so with the kind of switching between them, formally speaking.
Mm-hmm. And so if I can follow quickly, if it's not really this, it's more like different parts of the world, does it lead to some kind of form of model realism of multiverse, or necessarily like you have the model structure and you have some kind of pockets, categorical pockets inside the model structure? Is that, do we have to go in that direction, or not necessarily?
I don't think it goes in the direction of modal realism. Modal realism, I think, would be something like all possible modal structures exist. Whereas, I think that it's perfectly fine to say that our world has some specific modal structure. There are other possible modal structures which are not instantiated in our world. And so the various different sort of internal views on the modal structure of our world are constrained by the actual modal structure that we have, and not by modal structures in other worlds.
Mm-hmm. Okay, we'll follow up later. Thanks.
Thank you for the talk, very clear, but I'm a little bit dumb, so could you help me to understand what you mean exactly by model structure? Because at one point I thought, oh, there's a box there, okay, that's necessary, but at the end, with it's my idea, it's more counterfactual dependency, conditional counterfactual. If it's based on common cause, it's an analogy to common cause. So please help me. Because you use model structure all the time, and I have no idea what you're meaning exactly.
So, like, roughly speaking, the modal structure is, I guess, the way I understand the kind of structure that we seem to be dealing with in these kinds of theories. So, in this theory, the claim that we start from our big global state, and we obtain from it statements of the form persistive as in some state psi I relative to the problem UTI. So those things are like connected in some way. What is the nature of that connection? Not totally clear from the formalism, doesn't seem to be spatiotemporal. I want to suggest that a useful way to think about that is to think about it as encoding some kind of modal relation. which is enforced by the underlying mnemonic structure of that state.
But there's a difference to say it is necessary that this relation exists between these two variables, and it's different to say, like you said a little bit later, if this one was there, this one would be there. So it's not the same kind of model relation. So which one it is for you, according to your vision of the problem?
Yes, so as I said, I'm using the word modal very generally, so I'm not using modal to refer only to like literal necessity. I think about mnemonic structures as modal as well. So I think of this as being some kind of connection which is like weaker than logical necessity, but stronger than just contingent.
Some kind of physical necessity.
Yeah.
Thank you.
Thank you. That follow-up question with this discussion.
No.
Oh.
It's an independent question.
Ah, okay.
So there is a follow-up or I just...
No.
Can you say a bit more about why you characterize the partial observables as related to gauges? At some point you were saying that the complete observable is what the theory can predict and is the physical thing, which is fine. But the partial ones can be understood as related to specific gauges or controls.
I don't think if I said that, I didn't intend to say it.
Okay, then maybe I just misunderstood.
What did I say about partial observables?
Can
I'm sure, let's go see what I intended to say about partial observables.
Oh yeah, it was in the quote, just past afterwards. Yeah.
Oh, I didn't read
So
this.
it was
This was someone else.
It was from Dean, huh?
Yes.
So maybe he's the one that I should ask the question to.
Yes.
Is it the partial observable correspond to an arbitrary choice of gauge
Yeah.
that we transform away? I'm not really sure what is meant.
I think probably what he is saying here is that the partial observables are not invariant under diffeomorphism.
Which is fine, they are covariant. Yeah, the partial observable is the value of the field that you use in constructing the complete observable. So the thing that actually transforms is the value as a function of the point,
Yes.
which is, strictly speaking, is something else. It's not even itself a partial observable.
Yeah.
So, but, okay,
Yeah.
sure. I'll
Yeah.
ask the Dean in case.
Yeah, I agree that non-gauge invariant, so we're not going to say that.
Thank you. I think my question is very closely related to one that's just been discussed. It was also about the sense in which we can say that complete observables are, or well, represent modal structure. And then I think in response you said that the notion of modal structure that you employ here is a rather general one and a rather weak one as well.
Yeah.
And I was wondering whether the notion of modal structure that's at stake here is actually sufficiently similar to the modal structure that came up earlier in your discussion of the necessitarian approaches to Quiddities, whether these two senses of the structure that we have here is merely modal, how can we understand something actual emerging from there, whether these two senses of the structure being modal are sufficiently similar, if that makes sense as a question.
Yeah, I see what you mean. I guess my response there is that I think the way I characterized modal structures earlier in terms of, where is it? Yeah, if you think about modal structures as just describing possibility or something, I think that's just the wrong way to think about what modal structure is. And so I think that the partial complete observables formalism and so on are giving us different ways to understand what modal structure is in the actual world, in a world governed by laws sufficiently similar to ours, or where the partial complete observables formalism is correct. So that's kind of part of what I mean when I say I'm not convinced that it's useful to try to study the relation between modal and non-modal features in complete generality in a way that's like independent of what the laws actually like, because different types of laws are going to tell you different things about the relations between modal and non-modal features. Does this make sense?
I think think so. So just to check if I understood what you said.
Yeah.
So that seems to imply that when you say that the partial observables, complete observables framework, or the reference frame framework helps us solve this conceptual puzzle of the emergence of something actual from something purely modal,
Yeah.
part of that solution consists in a refinement of the notion of modal that's at play in the first place.
Yes, exactly. I think that the perhaps vague picture of modal structures as being just about possibility in some sense is too vague, and the partial complete observables formalism gives us a more robust notion of what a modal structure might be, and in that picture we can see hopefully clearly how non-modal stuff could emerge from this kind of structure.
Okay.
Any other questions? Otherwise, I'm jumping for one. This is quite interesting. There was clearly not one very quick thing. I think when you introduced internal view, you briefly mentioned rationalism as an option. And I was sort of curious as to whether or not some of the tools, some of the stuff that you were saying when they discuss relationalism might actually really help here. In the following sense, so sometimes people characterize relationalism as a view that is committed to stuff like the actual locations of material objects and their possible locations in order to recover things like space-time points, for example, to recover logic, there's logical construction, things like space-time points. And I was sort of curious if you could not say something similar here about some of these quantum reference frame things. So you could say something like, these are just collection of sort of possible clocks or possible time stuff that's happening in pairs. And then moving to what you call the internal view just consists of picking one of them as actual or whatever, where you're going to understand actually in a sufficiently weak way that it's not going to prejudice anything of what you say. And if that might not be maybe an easier way to characterize some of the modal-non-modal connection that you're doing on that compared to stuff like common ground, for example.
Yeah, I guess I am personally reluctant to go down that route because I do not want to say that adopting one internal reference frame means that's the only actual one. Partly because I think it's really important to account for and take seriously the relationships between different internal views. I think a lot of the science is in those relations, and so you need to be able to kind of treat them all on a level as, in some sense, as all actual. So that I think is why I'm worried about that.
The way I was thinking about it was that you could use like an indexical construction of actuality that might allow you then to move across. Like it's one where it's not robust enough that it's gonna, but
sure.
Fair enough, it's still gonna be.
Yeah, I can see that, but I guess I would want to be able to be like in my own internal reference frame and still acknowledge the reality of everybody else's reference frame and the connections between them.
Any other questions?
Yes, I do. So thank you very much for the presentation. It was great. I was wondering whether you could expand a bit on how you would relate different representations across different internal views. So it looks as if this quantum reference frame and the page filter mechanism is cast can be cast in different ways. And so I was wondering, are there contexts in which the passage from one internal representation to another is non-trivial, and then which kind of outcomes would you get from that?
Yeah, great.
Case.
So I mean, that's one of the main things the quantum reference frame formalism wants to study is precisely how do you translate between different internal reference frames. Formally speaking, you would often do that by going via the global state. So you translate from your internal reference frame back to the global state and then to the other one. And there's, there are a whole bunch of formal mathematical results characterizing what those transformations look like and what happens when you do them. You in fact find all sorts of quite surprising results, so things like the presence of entanglement, the presence of superposition, and even the subsystem decompositions all turn out to be relative to your choice of internal reference frame. So roughly what this picture tells us is that a lot more of our physical descriptions are kind of relational in the sense than we might have naively assumed. So yeah, there's a lot of quite interesting physics in those translations between reference frames.
But I know that it's not always the case that you can pass from the internal representation, say, to this global one, right? So as long as these internal reference frames that you use to parameterize the evolution, say, of the other degrees of freedom, start to have some, I don't know, gravitational interaction, then you may have some complication in the formalism. So I was wondering, in that more complex and more physically realistic situation, which kind of lesson should we learn about this form of modal structural realism?
Yeah, I guess my expectation would be that for any two physical reference frames, it will ultimately be possible to translate between them, because I believe that we all live in the same world and we are connected in various ways, so there must be a translation. I think that the formalism has not yet developed far enough to be able to cover all possible cases, but I would expect that, at least in principle, it's always possible to make that translation. It's certainly the case that there may well be certain sort of features of one representation that don't translate nicely into a sort of simple thing in another representation. So there might be cases in which one perspective is too alien to another perspective to be like have a sort of straightforward characterization of what that relation is. But I would expect that at least at a sort of mathematical formal level, there would always be a translation.
Okay, thank you.
Any last question? Then we can have a break, and I suggest we meet present back again. Let's meet back again at 16:15 with Daniel's talk.